back to your question again. Sorry about that. So you have this yeah, the solid line will be the standing wave as you see it now. Then in half a period's time, it will become like that. Okay, but this is like the shape. This is like the graph of the. This is like the graph of the standing wave, right? It is not the actual positions of the particles. Now, if it's a string wave, if you had a string wave like this, right? If you had a string, right, and then you did a wave on the string, you would see the string like do a standing wave like that. Okay, you will see a standing wave, something like that maybe. Okay, and then you can draw the dotted lines. Now that will be exactly the part where the particles are. The shape of like the wave is where the particles are. You get what I'm saying? But this is only for string wave, right? Because the string particles make the shape of the wave, and the shape of the wave looks like looks like this. It literally looks like this. But then when you talk about sound waves, this is a sound wave, right? Okay, a sound wave. When you talk about sound wave, what you're looking at, this blue color line here, this is actually the wave shape. It's a graph. It's a graph of its displacement against the position of where the particles are along the pipe. But it doesn't really show you where the particles are. Like the air particles are not like all gathered up here, right? And then it's not like all like gathered down here like this. It's not like that. Okay. So you may have to go and recall one of the things that I did previously, which was like the particles and wave shape of a longitudinal wave, right? For sound wave. So you may have to request for my year 3 4 videos, right? Longitudinal, right, wave videos, okay, where I explain where the particles are, because I believe I might not have done that in a lot of detail in the C4 videos I sent you, right? Maybe even in the C4 videos, I also told the students that you may have to go and refer to my year 3 4 longitudinal wave video. So if you have to ask me for that, you better ask me for it. Okay. So the thing is, these right, for sound waves, for these standing sound wave in the pipe, these are actually just graphs only. They show you the displacement. Okay. So the question is like, oh, what displacement is it then? So you got to imagine that there's an equilibrium line in the middle, right? There's an equilibrium line in the middle. And any positive amplitude, any particles with a positive amplitude, right? We consider that as moving to the right. And then any negative amplitude, which is like you can see here, we consider the particles moving to the left. Okay. So if I were to locate particles inside this column here, right? Inside this column here, if I draw all these red dots as particles, okay, all these red dots as particles, then we have to draw like arrows to show their movement, okay, to show their where. Okay, so if you see, right, I've drawn all these particles at like even intervals. So this indicates like this is probably like oh, how they look like before a standing wave existed. This is kind of like how the particles are equilibrium, right? How these all these particles are equilibrium. Okay. um So, but then, once the standing wave goes in, or rather, once the sound wave goes in and it creates a standing wave, then all your particles will start to have displacement, right? So the graph, the blue color line graph, shows you the displacement. Anything that's positive above the middle line is positive displacement to the right. Anything that's negative is negative displacement to the left, which also means that I can now start drawing arrows, right, to show the displacement. Okay. Right. So yeah, lah, I mean, just trying to show the yeah, right, trying to show the displacement of that. So you see, right now, right, when the graph looks like this, particles on this side have positive displacement, particles on this side have negative displacement. Okay. Then in let's say half a wave time, right, in half a wave, right? That means this will now be the graph, right? The graph will look like this, but it also means that the particles all have reversed their, like, they have a reverse displacement now. Okay, that means that the particles, right, with like this, so they will start having arrows that looks like this. Okay, yeah, right. Is that what your question was? Yeah. Mm. Okay. Okay. Hang on. Let me. Huh? Okay. Oh, not that it creates no, not that it creates a node in the middle. The node was created. It was created because of the standing wave, right? Nodes, anti-nodes and nodes are created due to standing waves, right? Right. So it's a matter of how they move, right? Okay. I think the best thing to do now is to show you that GIF. Hang on. I'm pretty sure I would have shown you the GIF anyway, so but just let me get there first, okay? Well, I don't even know whether or not I have a copy of that in my, hang on. C4, right? Yeah, I don't even have the, oh okay, I know, I do. Right. So it's kind of like you have to start off with this first, right? The um the standing wave was created when the wave was traveling back and forth, right? Which then nodes and anti-nodes are created. So it's not, the nodes were not created because of the movement of the particles, right? The movement like the movement of particles on the left side and right side, like the nodes were not created because of that. Like, the nodes were created because of how would I put it? Hang on, let me just think about this first. Let me think about how to say it to you. Okay, the nodes were created because once a standing wave is created, right, there will be regions where the particles have no displacement, and this guy in particular has no displacement. All right, so the particles will move like away and towards, away and towards, but this particle doesn't not move because of the particles around it. He doesn't move because that's where the node was created when the sound wave was reflected and create a superposition there. You get what I'm saying? Yeah. No. Hang on. Like you gotta ask yourself, like, what is a compression? What is a compression? So when the particles goes towards each other, when they move towards each other, it becomes a compression. You got what I'm saying? Yeah. So it just so happens that this is how, right? This is how the particles move, right? They move back and they move, like, away and towards, away and towards. So when they happen to move towards, that's a compression. This is rarefaction, compression, rarefaction, compression, rarefaction again. You know? Yeah. So it's kind of like, it's a it's not because of this then that. It's more like it happens to be the node, it happens to be the particle that's not moving. The particles around him are moving, they move this way, they move away and they move towards. Then you can say that, oh, I get compression when they move towards, and they get a rarefaction when they move away. Okay? Yeah. So that means that if, let's say, I ask you, right, okay, what can you describe about a node particle? A node particle would be a particle that is sometimes in the middle of a compression, sometimes in the middle of a rarefaction, right? But it's not due to the node particle. It's not like, oh, the node will make a compression, the node will make a rarefaction. No, it's not that. It's basically this picture here showing you how the particles move, like the way they move, and therefore it creates a compression and it creates the rarefaction, right? And the node just happened to be in the middle of it. Yeah. Okay. And I mean, and also at the same time, right, when you look at the graph, right, you see this guy, like, he has zero displacement like this. Okay. So depending on how the curve shapes, I think I mentioned this in the recorded lesson. Depending on how the curve shapes, right, that's how that's where the particles are, how the particles are behaving, lah. Yeah, right. So I mean, if you want, I can't really slow down a GIF, but if you really really want to slow down I don't know whether you can slow down a GIF. But you see, okay, you follow this finger of mine, this one. This guy's moving back and forth, right? Okay, sorry. Moving left, right, and left, right? Okay, right, and then left. So what happens is that you see, like, the corresponding graph would be like the particle here will be here. So when he moves right, he's positive displacement, left negative, right positive, left negative. So this graph is drawing the graph of how the particles move. Yeah. At higher level questions, which I think I also I also mentioned to you, was like, oh, if I had a particle here, right? Like, at the particle here, like, what's he in the middle of now? Is he in the middle of a rarefaction, or is he in the middle of a compression now? Like when the graph is like that. Ah, right. So you're supposed to go and work it out, right? Sorry, what? It's a rarefaction, good, because you're supposed to look at the neighbors, right? Yeah, you're supposed to look at the neighbors. So these particles on the sides here, these particles on this side here. So the particles on his right side have positive displacement. Particles on the left side have negative displacement. So particles on the left side, right side move to the right. Particles on the left side move to the left. So therefore, right now it's a rarefaction because the graph shows you that they have moved, right? The graph shows you that they have moved where, right? They have moved to the left and to the right like this. So they move this side and they move this side. So right now it's a rarefaction. Yep. Okay. Anyone else with a question? Who? Okay. What question do you want? Oh, you're copying this down, huh? C5. Doppler effect. Yeah. What's up? Those are very strange questions. Your means is who? Your is me. Okay. Wait. Hang on. There are three things, right? For Doppler, right? I mean, what are the? Okay. Hang on. So this C5. Okay. C5 for Doppler effect. And are you talking about sound, or are you talking about EM wave? Sound Doppler. Okay, sound Doppler. All right. There are three things. You have an observer, you have the source, right? I mean, it might be a car, it might be something, I don't know. So there's an observer and there's a source, right? Okay. And then the source will emit the wave, the sound wave, right? That's the guy. Okay. So these are the three things. You got your observer, the source, and the sound. Okay, who's moving? It depends on who's moving, right? That's like the most important part. Like, you got to tell me who's moving. Sure. I understand. Sometimes, right? Yes, you're absolutely right. Sometimes, but the sometimes depends on who's moving. So who's moving? Like, you're asking me. You're asking me. how come sometimes, right? I'm telling you how come sometimes now. Because it depends on who's moving. So who's moving? Which one do you want? Okay, then hold on, observer moving. So, I mean, observer moving, you can use this equation, right? So there you go, right? Okay. But do you remember in my notes, I think I made a like a kind of like a point. Hang on, Let me just pull out the notes first. Okay, so sound, right? Sound, right? Okay. No, observer is moving. You see that? And you see this? Okay. So if the observer is moving towards or away, if the observer is moving, right, what is changing? The speed of sound is perceived to either increase or decrease while the wavelength remains constant. Is that what? Okay, so that's another question on its own, right? Because if you ask me, if you were asking me like, oh, how come it changes sometimes? How come it doesn't change? Right? This is the reason why, right? So when the source is moving, the wavelength seems to change because you look at these circles here. Do you not see that the gaps between the circles getting smaller and smaller, right? And this on this side here it gets bigger and bigger. Yeah. So basically, the wavelength is perceived to change because the source is moving. But this one here, the source is not moving. The source of the sound is staying there. So the waves that he's sending out, right? Right, he's not chasing the waves in any direction. So the waves he's sending out all have a constant wavelength, right? Yeah, I mean that's the reason why. Oh, hang on, I just want to point out to you. Do you know why I say memorize? Because they have asked this before. Like, if the source is not moving, what doesn't change? Yeah. So if you don't memorize this, then I mean, you're just disadvantaging yourself, right? Okay, okay. Now you can ask. What's the question you want to ask? Let's say you are what? You're running towards the source. Is the source moving? Okay, so something like that. Yeah. Okay. No, but you're not the one producing the sound. You're passing by the waves, right? Okay, you're not accelerating. All these questions here, you're not accelerating. So you're passing by the wave fronts at a constant rate. You can't accelerate. So any acceleration of these kind of like you look at this, these are all constant velocities. Constant velocity, constant velocity, constant velocity, constant velocity, constant velocity. Right? There was only one instance when I was doing acceleration, and that was a graph of the train that was accelerating towards the platform observer, right? Right? Then you have to draw the graph. Yeah, but that's the only time that you have to worry about, like, if it accelerates. But no, yeah. So you're thinking that if you pass by the wave fronts, it seems to get shorter. No. Like, you pass by the wave fronts, it probably might seem shorter to you. It probably might seem shorter to you, but it's consistently that short. So no matter what, the wavelength is still perceived as constant. The equation here helps you to correct for that thing there. Yeah. Yep. Yep. But you see, the thing is like how we understand this in the first place is actually from the source, not about the observer. If the source is moving, if the source is this one moving to the right side, then you can see that he's chasing his wave fronts, right? So as the wavefronts are being chased, the space between the wavefronts gets smaller and smaller, right? Yeah. Like like when we say that the wavelength remains constant, right? We're talking about like the legit wavelengths are not have not changed. Like if you can see wave fronts in front of you, right, you see that the wave fronts are equally spaced. Yeah. The actual wavelength. Yeah, we're talking about the actual wavelength. We're not talking about like the perceived wavelength in a sense. Yeah, yeah. Yeah. That's the thing you're supposed to memorize. Yeah. There's no, I mean, you can try to understand it, but even after you understand it, if you don't memorize it, you're gonna lose the mark for this because they're gonna ask you. I mean, there's been quite a number of questions where they ask you like, oh, what happens when, you know, yeah. That's all the question you have. All right. Um, anyone else? C3, yeah. It's okay, dude. Like. I mean, I'm holding this session for you guys, right? So if you gotta have to ask, you gotta have to ask, and just, I mean, I don't have an agenda here. Like it's supposed to be a consult, you know. I like this is not. I don't know, man. A lot of people always think that oh, Sam's gonna hold a crash course. No, I'm not. Ah, why am I holding a crash course? I sent you all the videos. Ah, you get what I'm saying? Like I literally sent you all the videos, guys. I'm not gonna hold a crash course for what? Like, yeah. Okay, what was it? What's this then? This one? Oh, 13. Okay. What happened to the energy carried by each pulse? Each pulse. Sorry, what is it? The answer is this? Yeah. I guess the like when we cancel each other out, right? When the pulses cancel each other out, it's not like it will. It's here's the thing. It's not like the energy will disappear. We didn't destroy energy, right? So what happens is that the it will still continue, but it will still travel like yeah. Mm-hmm. No, I would say that the okay. Hang on, let me think about this first. What is sound really? Like when we hear sound, let's say we talk about sound, right? When we hear sound, what is sound really? Sound really is compressions and refractions, right? Okay, they are just coordinated vibrations of air particles. Do you understand what I'm saying? Coordinated vibrations of air particles. Okay, so if let's say you have two sound waves traveling towards each other, one anti-phase, one in phase. Okay, sorry, one original phase, one anti-phase, and they meet, right? They kind of like they cancel each other out, right? The particles are actually still vibrating. Like the energy of the particles, the energy of the pulses are still they still exist as kinetic energy of the particles, but you just don't have that pattern of compressions and refraction, so you don't hear sound anymore when they interfere and they do destructive interference for that moment, for that region where you're at. The particles are still vibrating, but there's basically no formation of compressions and refractions. The energy is still being transferred through the particles, and eventually the two pulses will separate, right? So when two pulses meet, they cancel each other out, but then they will still you know so it's not like the energy disappear. The energy cannot disappear, so they end up being like vibrations of particles. Yeah. Really? Really, man? Oh, sure. I mean, oh, I didn't know that. Oh, where's my Telegram opening? C3, is it? Oh, C4 and C5. I got a Feb 19. Okay, C4, C5. Okay, C4, C4. Where? C4 final, C5. Okay. Whoa, C4 is how many parts? Shit. What's that C4 part for? That's crazy. C4. Wait, not C4 Saturday lah. Huh? Then what's that part for? I don't know what part for is. And then I have a C4 final, C5 final. Oh, C5 seems to be very short. Okay, let me just double check the links. Oh, why do I see my face everywhere? Oh gosh. This is C4. No, wait, hang on. This is C4. This is C4 Saturday. So something like that. When do you learn? When did they teach you C4, guys? In school? In Feb. So it's basically when. Hang on. Why did I say part 4? That's not part 4. That's just part 2. And then there's damping. Oh, there's resonance and damping. Is there resonance and damping? Standing waves, free oscillation, forced oscillations, damping. So that's part 2. Sorry, hang on. I mean I'm doing this just in case I forget. Oh, C4 another time I said that. C4 part 1. You gotta remind me these things, man. C4 part 2. Uh, it's supposed to be part 2. Why is it called part 4? It's not part 4, part 2. Part 2. Uh, okay. And then there's the 4 final and Doppler, right? 5, right? Did I finish 5 in one lesson? Okay. I finished C5 in one lesson. That's crazy, man. C4 final, C5 final. There was only one lesson and only. Hey, there we go. Okay. Yeah, remember to like and follow, guys. Why do you have to go slow? What you want me to do here? What's this? Oh no, 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 no. Wait, hold on. Do you? Whoa, whoa, whoa. Hang on, hang on. That was a bit confusing. Okay, okay. Firstly, okay. Which chapter is this? Okay, not bad. This is C3. Uh okay, I think you got the wrong concept here. This is modulation. This is modulation. The concept being tested here is modulation. Um, yeah, it's where the single slit first minima is, yeah, the envelope, the minima is coinciding with the fourth one. This, well, I never saw this question before, but I didn't realize that they just kind of like they condensed it into one small thing. Um, it's a this one. Yeah, this one. Yeah. So instead, wow, this question also a bit asshole, right? Sorry, but it's like I mean I know it's my homework, but it came from a textbook, so I'm just telling you, right? So whatever they describe here, blah 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 blah, is basically being, yeah, shown here like this. So yeah, so basically the fourth interference is the fourth peak is missing because it envelope, the first minimum is coinciding, the first minimum of the single slit is coinciding with it. Yeah. Wait, what? Yes, that's right. No, no. What are you talking about? What minimal diffraction grading? No, no, no. There's no diffraction grading. Okay, I mean, okay, fine. So this one here is double slit, right? Double slit with uh single slit modulation, correct? Modulated by single slit, right? Double slit modulated by single slit. All right. So what happens is that um like for example this one here, which peak is missing? This is 0, this is 1, this is 2, this is 3. The fourth peak is missing. It's the same thing, right? It's the same idea. The fourth peak of the double slit is missing. It should be there, but it's not there. So the minima of the first slit, the minima of the single slit, the pattern, has coincided with the fourth maxima of the double slit. Yeah, this one is um, first minima of single slit envelope has coincided with fourth maxima of double slit pattern. Therefore, missing. Right? But for the question you sent me, they're talking about what? They're talking about a multiple slit, right? So it's essentially the same thing, right? So essentially the same thing. It's just that we change this to multiple slit pattern. Yeah, yeah. Coincided with the, yeah. Okay. So diffraction grating supposed to have modulation as well, which is here, bro. This one here. This is you see, modulation also affects multiple slit diffraction patterns. So this one here. Okay, so for example, this one, which one is missing? Yeah, correct. The third one is missing. Okay, good. Get out here. Is that your only question left? Is that it? Okay. Then I'll just stare at the rest of them now. Okay, bye. Hello, the rest of you. What? Ah? Oh, hang on. Shoots. Where is it? Yeah. Why? Oh, you wanna see his question, is it? Alamak, where's Jonathan's chat? Joanna. Yeah, what's up? Hmm. Yeah. No, it doesn't matter. Yeah. Okay. I mean, modulation is usually more troublesome, so I'm okay to go through this. Yeah, but for the other stuff, you probably have to, like go back to the video. So you already know that I already sent it out, right? The C3 lah, basically. Oh yeah, we did it on this thing. Yeah, we did it. Okay, but it's okay. It's okay. I'll go through it again. I'll go through it again. It's fine. It's chill. Um, because I mean I did it for double slit. I did it for double slit. I didn't really do it for multiple slit. So I'm gonna do it for multiple slit now. Okay. Right. See what D3 Okay. Did they give you any practices to do? Oh shoot. You know what? You know what? You know what? You know what? My dude has come up with all the past year questions. Like he has been pulling out all the past year questions for me. Hang on. Hang on. I'm pull out his work. But hang on, Duran, I will. Sorry, not Duran. The mayor one. I will. Okay, there we go. Wait, hold on. What is it? C3, is it? So something like that. Wait, this kind. Yeah. Hang on. Let me just double check everything first. Hmm. Right, interference, right? So the dude has helped me cut all the way May 19, all the way 18. Now, because I haven't checked his work yet, so I'm just making use of this opportunity to check his work. 16. Oh, then no 17. Was it 17? Yeah, there was 17. Pretty much. Oh yeah, but all these are all May papers only. So these are all the May papers. Yeah, I'm just asking him to cut all the May papers for me. I have yearly papers for you guys as well to prepare for end of year. Yeah, because I got him to go and cut all this. But yeah, like modulation this one. Something like that, right? Okay. This one will be, you see, monochromatic light incident normally on 14 parallel rectangular slits. So this is multiple slits, multiple slits. Then do you understand that multiple slit pattern is supposed to look like this? But because there's modulation, so kind of like the 0, 1, 2, the third peak is missing, right? The third peak is missing. Yeah. Okay. Cool. Right. So yeah. Okay. Yeah. Hang on. Let's do this now. So multiple slit, but I make the slits a little bit thicker to show you that it's not ideal, right? Something like that. Okay. You know what? I'm just gonna use that picture over there, and then you get a pattern that looks like this on the screen. Right. So your screen pattern looks something like that, right? Oh, shoot, sorry. Right, you will have a bright fringe in the middle. Oh, sorry. You have a bright fringe in the middle like this. Well, it's actually going to be a point here. It's a very strong point. Okay. Then slightly weaker point. Then kind of weak point. Right? And then afterwards, there will be like a gap before the last fringe appears again. Something like that. Right? So this is like the this is like the 0. This is the 1. This is the 2. This is a 3 that's missing, and that's the 4 over there. Do you see the 4 over there? Like, it's supposed, like, it's a super weak one, right? The 3 is missing, right? The two is actually a bit brighter than the 4, so maybe it's something like that. Okay, something like this. Okay, but still, hang on. Yeah, something like that. Okay, so this is the 0, this is the 1, this is the 2, the 3 is missing, and then the 4 is there. Okay, and then you have that laser light that's going in, right? Like the laser light that's going in to the slits like this, right? Okay. I mean, I show one beam of laser, but I kind of like exaggerate the size of the slits, right? Okay. So single slit, I'm gonna use the blue, right? Single slit, I'm gonna use the blue one here like this, right? You see the blue one there? Yeah, that's a single slit. Okay. Now, so the question is this: what's the single slit equation? Okay, I mean, we are allowed to use the data booklet, right? Okay. So C3, right? C3. Yeah, C3. Yeah. Oh, yeah. You wait, okay. Let's. Shoots. Okay. Well. Um. This sucks. Wait, hold on. Okay. This one. Okay. What equation did you say again for single slit? Absolutely wrong. Yeah. Now, dude. Yeah. This for diffraction grating. Yeah. It is. It is. You would use n lambda equals to d sine theta for the multiple slits, which gives you your pattern here. This pattern here. The bright fringe. This bright fringe. This bright fringe. Okay. So I backtrack a bit. I backtrack a bit. So you need to understand. You need to understand the backtrack a bit. So if let's say you had ideal diffraction gratings, which means that the slits are very narrow, right? Okay. What sort of pattern will you see when you shine the light in, right? You will get fringes. You will get the exact same positions as what we do here, as what we get here, but all of them are all almost equally bright, like that. You see that? This is non-modulated. This is ideal diffraction grating. This is ideal multiple slit. But because of modulation, you get a pattern that look like that. Okay. So if let's say they give you this, right? Okay, I erase the blue color thing for now. If they give you this picture and they ask you, can you suggest how the original ideal non-modulated multiple slit pattern looks like, right? On this graph here, then you know how you have to draw? You probably have to draw something that looks like this. Wait, don't okay me, because there's a couple of reasons. There's a couple of things that's kind of important for you to take note of. So ideal means all of them equally bright. Correct? Oh, sorry. This is multiple slit. This is not double slit. Sorry, I made a mistake. So it kind of like should look like this. Hang on. It's supposed to be like completely black in the middle. That means completely dark fringe in the middle like this. You know what I'm saying? So it's supposed to look like this. Ideal is supposed to look like that, right? So they're all even. Okay? They're all even like this. But notice how I intentionally drew them a little bit lower. I mean, like quite low compared to the to this. Yeah, why? Yeah, why? No, it's because right, like what makes the difference between non-modulated and modulated? Like what's the big difference between these two? Right? This one wider slit, right? So are you agreeing with me that once the slits are wider, that you get modulation, right? But wider slits also means more light passing through. So the modulated pattern, right, will always be brighter than the non-modulated one. The non-modulated one will be like the even brightness, but they are all about quite low because the slits are very narrow. So they originally look like this. Then when you go and widen the slits like this, right? You go and widen the slits a little bit like this, right? Right. What's gonna happen is that all these patterns here, they all will start to increase in intensity, but then they will start forming this envelope thing. This so there's two things happening. Number one, it gets brighter because like the slits are wider, right? It becomes wider like this. So these intensities here will all start to increase, but then the ones on the side here will start to decrease here like this because there's that envelope thing that you have to deal with. Yeah, yeah. Okay, hang on, but I'm not done yet. So that's the I did the backtrack. So now I'm back to here again, right? So back to this idea. So this is the single slit envelope, right? Single slit envelope. Okay, so the single slit envelope is based on what? What's the equation? You told me d sine theta equals n lambda, right? And I told you that's wrong because this equation is meant for the is meant for diffraction grating, right? This equation is meant for the diffraction grating. Like it's meant for it's meant this equation is meant for these peaks, right? Maybe I should color code it differently. Like so diffraction grating, going to use red. I'm going to show you to you in red. Right. This is for the diffraction grating maxima. Okay. Wait. Okay. I don't know. I'll check later. Yeah. Yeah. Okay. Um. Sorry. You were saying? Huh? Oh. Where do you get that from? School. School notes, right? Okay. Okay. School notes. But in any case, right? I mean, school notes is school notes. You can never bring your school notes to school to the exam, so you have to rely on your data booklet, right? Is this one? That's the single slit. Yeah. This is the single slit equation. So this envelope is based on these equations. Theta equals to lambda over b. You get what I'm saying? Like the envelope, the theta, there's basically what this question is saying that the angle to the first minima of the single slit pattern, right, is yeah, yeah, is theta. But this is theta single slit. You get what I'm saying? Okay, wait. Hold on. Lambda is what? What's lambda? Wavelength, right? So wavelength of this light. This is the wavelength, right? But what's B though? Slit width. So we are talking about like how wide these slits are, like this. You see, like how thick the slits are. You get what I'm saying? Okay. What's the equation for diffraction grating? This one, right? Okay, n lambda equals to d sine theta, right? So let me write that in red. So d sine theta equals to n lambda, right? Like shoot, what's this? Okay, so d sine theta equals to n lambda. Right, lambda is this lambda. I mean, it's the same lambda, right? N will be what? N will be the order, right? So this is like n equals to 0, n equals to 1, n equals to 2, right? That sort of thing, right? Okay. The theta though, for multiple slit for diffraction grating, the theta is what? The theta is the angle between the 0 and the nth maxima that you're using. Yeah, for this case, it will be the third one, right? Wait, actually, you know what? I just realized that maybe I may have made a mistake here. It kind of looks like the third one is still there. Sorry, I just realized that I just see that there is a very faint one here like this. You see that? There's like a very faint dude here like this. I'm sorry, that's the third one, right? So the fourth one is the missing one and the fifth one is there. So it kind of like there's a very faint third one, right? There's a very faint third one and the fourth one is missing. So the fifth one is like reappears again later on. Like that's the fifth one there, right? So the fourth one is missing. So it's basically the same as the original question itself, like Jonathan's question. Yeah, the fourth peak is missing. Yeah. Okay. So then you got to understand that d sine theta equation, this equation is meant for these peaks, this red one, this this ones here. Yeah, that's the equation for that one. You get what I'm saying? Yeah, but what is d though? Distance between the slits. No, small d, bro. Between the slits. So this is it, right? So what was Jonathan's question? Like, after all that, right? Like I know it took 15 minutes, right? But after all that, Jonathan's question was what? What was his question? His question was, he didn't forward the question, right? The fool. Ah, let me just hang on. Let me just forward it to the. Yeah. So based on his question was asking this, right? He's saying that multiple slit arrangement, slit width is this, and it goes to 4, interference maximum is missing. What is the separation of the slits? There's what's D? Yeah. Okay. Right. So the big problem I'm facing now is this, right? This is the diffraction equation this is the diffraction equation, this one here, right? He's saying that the fourth peak is missing, so d sine theta equals to 4 lambda, correct? Yeah, but then you see, right, single slit, the equation in the data booklet um doesn't have sign, right? Yeah. So in fact, right, whatever you just said just now, your school's equation was correct. It will be sine theta single slit equals to lambda over b. So of course now the question is how come the IB data booklet, right, is showing you this, right? There's no sign. Small angle approximation. So technically speaking, we can approximate it to theta equals to lambda over b. So what your school's notes is saying, right? Because I mean, this telling you what's the rationale behind it, right? What your school's note is saying is that you have to um choose the appropriate moment to bring the sine theta back again. Yeah, that's right. Okay. So it turns out that, um so this is theta double slit, right? Okay, hang on, no, this is not double slit, this is diffraction grating, right? Okay, so sine theta diffraction grating equals to 4 lambda over d, right? Isn't this answer? Okay. No, as in like this is the manipulation of this equation here, right? Like I manipulate from this one to this one. Then on the other side, this is sine theta as single slit equals to lambda over b, right? Yeah, lambda over b. Okay, hang on, right. The thing is, sine theta of the diffraction grating is for the fourth order, which is basically four times of that. Yeah, let me think first. Oh yeah, oh okay, okay. Yeah. So these two angles are equal. Yeah, this angle is equal to this angle here. Yeah. So 4 lambda, yeah, so 4 lambda over d is equals to lambda over b. Yeah. Which is why d is equals to 4 times of b. Yeah. Which is the answer lah, right? He was saying that that's the answer, right? Yeah. Distance is equals 4 times of b down here. Yeah. Okay. Yeah, sorry. I mean, all that just to explain that. I guess I understand, but I think I covered quite an in-depth, like, understanding of what modulation does lah. Yeah. Okay. Any further questions? Hey guys, any further questions? Okay. I will upload that file for you guys. Okay. But that's a lot of files. I need to upload for what again? C3, C4, C5, is it? I need to upload for C3, C4, C5. And what else again? D3 and D4, is that right? D3 and D4. Okay. I mean, you don't have to do all. Maybe you can just choose to do like maybe a particular year. Maybe you just choose like one of the May 17 and you just do the May 17 or something like that. I would rather you do like one question from each of them, right? Rather than you try to do everything from one folder, because I think you'll just overwhelm yourself. Yeah. Um. Say what? Yeah, correct, correct, correct. But they have to go through all the files, right? So if let's say for example you go into induction, then you go to paper two, you know, yeah, then you do the or maybe you go paper one, I don't know, paper one. Where the where's the answer? Where's the answer? Uh-oh, I think he didn't give me the answers. Oh no, there are answers. Wait, hang on. Oh, I think he gave me answers in another place. Wait, okay. I will have to go and put answers down for you as well. So this is default lah, right? This is all the induction questions. Questions always look a bit more interesting. Like, I mean, if I'm talking about like from a teacher psychological point of view, right? I'll be like looking at this, I'll be like, this is interesting, You see all these kind of different questions you can get. Yeah. Okay, I'm trying to catch up on the recordings. Just I would say just jump straight in. Like okay, like I say, I think Meapan was asking me, right? Like yeah, just choose like 17. Let's say for example you choose year 17, right? So anything that you see May 17, right, you go in and do it. Yeah. Yeah. Okay, thank you, bye.